right now we've got Dornfest giving a talk about string theory. Is that correct?
No.
No.
The talk is titled GR with a spin.
Okay.
And so we're going to be adding torsion to Einstein's field equations, and we're definitely not going to be able to get to all the cool explanations and intriguing ideas from torsion that we'd like to, but you guys can feel free to ask me about it at the end. And basically, as a short introduction, as Andres starts writing web vectors and dual vectors and dot products are on the board.
Just to save time on the equations.
Yeah, so basically, I'm a physics major at Berkeley. I'm an undergraduate, and I noticed that I was having difficulty being rigorous. I was always using analogies and ideas and phrases that made people that were very rigorously minded kind of scratch their heads and be like, wait, what do you mean? And so, for example, I would say stuff like, well, instead of saying a regular derivative, I'd call it a normal derivative. It's just a normal derivative. Like, well, wait, that's different. No, it's just a normal derivative from single variable calculus. So ideas like that, that's why I enrolled in the DRP program, and the textbook we used was
Geometry and topology.
yeah, Geometry, Topology, and Physics by Nakahara. Alright, so our basic idea is that we want to be able to describe motion, and we want to be able to do it in a curved space-time. That means the manifolds we'll be living in are dimension 4, but in general relativity was written in a way that is generalizable to any dimension, which is really good for people that want to do string theory. In physics, we would like to call these laws working out no matter what coordinate system we're in or reference frame we're in. We were talking to Einstein as Lorentz invariant laws. For the math department, you guys would call this diffeomorphism invariance. But what does that mean? Well, we have to start out from an idea that we have a manifold, we want some patch, we want to be able to extract information from it. The reals. So if I call this manifold dimension 4, and the reals are 4, we can define this as phi's of C, where that's a chart. This chart is going to be eventually generalized to the concept of being able to take multiple derivatives that are coordinate independent, forming many tangent spaces, and their connection all together is going to be called a tangent bundle. But first, let's just understand what vectors, dual vectors, and we'll go from there. So vectors, most people are used to seeing them with a hat on top or an arrow, but I'm going to write them with a raised into C. Dual vectors will correspondingly usually be written with an asterisk on the left-hand side, as being on the right-hand side often implies the complex conjugate. And we will write these with a lowered into C. Notice that I'm using the same indice here. However, in general relativity, indices are dummy indices. They mean nothing other than they're placeholders to explain your coordinate system or your operations. They don't necessarily have any connection to a specific coordinate system. It's just, if I asked you to think of a concept of color, a color would probably pop into your head. For me, it's blue and then yellow. Who knew that I was going to Cal Berkeley? So, generally, we like to be able to talk about the dot product V dot W, and looks like everyone in the room probably already knows this, but you can write this as the summation as VI, WI, or index I, and they add together. Well, I'm going to introduce something called Einstein's summation notation, which evidently does not exist in Evans Hall. But long story short, in 1910, Einstein didn't have LaTeX, and so he couldn't write functions to repeatedly write the same thing. So in all of his papers, he just erases the sigma. It's there, it's doing its thing, it's just no one wants to get their wrist cramping. So let's talk about what a contraction is now. Now that we understand the idea of a product within our vector space, we can then talk about the idea of what happens when I have VI, V sub j. Or, no, I'm sorry. V sub I, W sub I. From here, we can have a contraction, and this would mean that we cancel out both of these and we can get a product from them. Specifically, I'm going to be using today something that Andres warns me is jumping too far ahead, but you guys look like a smart group. So we're going to use the idea of something that will eventually look a lot like the concept that I'm going to call the metric. So from here, we're going to write V sub I, G, I, J, W, J. Now, here, we have a contraction. We have a repeated indices between the two i's. So this here becomes V sub j. Notice now that this dual vector, the lower indice, has now become a vector. Now the way I like to just think about it is that vectors and dual vectors are like matter and antimatter. When you combine them, they explode and they just turn into a bunch of energy. And similarly to how matter and antimatter can have certain properties totally different from energy, vectors and dual vectors, their product is different than usually themselves. And that goes into a whole thing called forms, like one forms, two forms, that I'm sure everyone in the room knows a little bit more than me about. So now we want to be able to talk about the definition of our derivative. Normally, we're going to be dealing with, or I should say, normally we have in our lives dealt with the normal definition derivative of a vector. The limit is epsilon goes to 0. Limits of t, where t is some arbitrary parameter. And this implies that we should be able to add and subtract vectors. Now, we should be able to all do that from linear algebra. We exist in some nice vector space which allows that. However, we're in space-time. We are not in a necessarily nice space. More correctly, we want this to be so general that we can arbitrarily assign it some type of connection between the motion and position of vectors within our manifold arbitrarily, no matter how curved or uncurved the space may be. This is going to be what allows Einstein to go from special relativity, which is in flat space-time, to his GR approximately 10 years later. Thanks to stealing off of a mathematician named Riemann, which we'll get to in a second. But, so, just for an example, if we look at this patch here, let's assume that it is arbitrarily curvy, and we take a two-dimensional slice of it. Just for illustrative purposes, let's say it looks like this. If we take the derivative at two different points, we may have a tangent space formed here and a tangent space formed here. We'll have an orthogonal vector. In physics, we like to call this a normal vector, or normalized if it has magnitude of 1, but what's important here is that it points out perpendicular to the tangent space. When I want to talk about adding and subtracting vectors that exist in possibly completely different vector spaces, it's a no-go given this definition of a derivative. So we need to introduce something more powerful. Therefore, let me write U sub A beta is equal to L alpha G V sub beta plus gamma alpha mu beta V mu. Notice the contraction of the vector with this, and notice how these do not contract. Specifically, I've now just introduced for you guys, and most of you are being very polite and not interrupting, asking what the heck this capital gamma is.
The previous talk actually did introduce what the capital gamma was.
Awesome.
Yeah.
Well, then I don't need to make the connection for you guys. But here, let me still write out what a connection coefficient is. Gamma, you can write as alpha beta is equal to 1/2 G mu sigma. This is going to go across the board. G sigma beta comma alpha. This comma is going to represent a nice little partial derivative. I'll write it out explicitly as soon as this entire expression is done. Sigma plus G alpha sigma comma beta minus G alpha beta comma sigma. Where now this comma is going to be representing partial sigma G alpha beta. Now, what's going to be important here for understanding what torsion is, similar to permutation of indices that we're used to. I use them a lot in classical mechanics to describe changing coordinate systems. We notice that sigma begins here and ends up in the back here, and we have differences here. What we can then therefore say is that this connection coefficient, this Christoffel symbol, is going to represent how our vectors, when we want to talk about transporting them in parallel or parallel transport, how they do so. But if they're on two different types of curves, how they do so relatedly and independently. So from this, we're almost here at GR. Let me write out one last important equation. And this one, I'm going to have to write out back in vector notation. So forgive me, it would take half the talk to write this whole thing out. And it's going to be based off a guy named Rishi. Now, I like to usually think of this heuristically as helping to describe the curvature of an object, but it's not. When you want to describe curvature specifically, you go to Rishi's tensor and scalar, where this is going to be R with the vector W is equal to here. Now the comma is going to be representing a commutation. I know physicists are horrible with our notation. Trust me, it's just as bad learning it as an undergraduate when I took grad GR last semester. Del B comma U back with our vector W. All right, so there we have all the components to be able to write out Einstein's field equations. And we've gone from linear algebra, for those of you joining, we've gone from, how much time do I have left? Someone?
3 to 4.
3 or 4 minutes. So in about 15 minutes, we've gone from linear algebra and single variable calculus all the way up to a nice and wonderful expression, which is what gives you the tides, what gives you night and day, what gives you this wonderful, beautiful December Berkeley weather. And just for everyone else in the room, c is the speed of light, g is Newton's constant that gives us the expression, F equals mg is equal to mm big G over r squared. And we're going to be able to write this as r mu nu minus 1/2 r g mu nu. And so in the last 2 minutes, I'm going to very quickly, as I run out of time, write out what this looks like as it has torsion in it. And the importance of this, I can answer as one quick question, or if you guys have a different one, you can always throw a curveball at me. But now we want to be able to write, this is why no one studies this. Partially so because one very smart guy named Cartan looked at Einstein's equations and noticed that you could talk about rotating reference frames that have to form an affine connection, meaning that they do not have a set coordinate system. They only talk about differences in vectors, such as I've talked about earlier in this lecture. There are billion terms in this, and it ends up being, I believe, if I remember, I would need to look at the paper I read this from again, but I believe there's 24 terms in here. So I'm not writing them all out. That is the beauty of the indices. Thank God we are not writing all the sigmas, capital sigmas out as well. But you guys should understand that adding this term in, as now you understand what the connection coefficient, this Christoffel symbol, means, and you understand the idea that these minuses and additions represent the relationships between our different vectors and curved spaces as they're parallel transported. These adding and subtractions represent how, in a rotating space-time coordinate frame, we want to be able to talk about how we can still parallel transport. This type of equation can both be related to quantum spin and therefore tie in both quantum field theory to angular momentum at a macroscopic scale. Now, it doesn't happen within very nice things, it happens within black holes, which leads to a very interesting proposition that I read a paper by Poplawski on, which I studied with my grad student. So I'll end my talk on this. Given this math and the fact that it works, there's no evidence for it yet, but it is totally possible that from a black hole, on the other side, a universe was born. Given that this black hole was rotating, as most black holes are observed to be doing, our universe would have a rotation as well. If you wanted to describe how motion becomes different than what Einstein observes, you would need to add in this, plus a heck of a lot more that I can't add. If you are interested in this is a 2006 paper by Alan Guth and Max Tegmark from MIT, which is excellent. In it, they predict whether or not you'll be able to observe this from Gravity Probe B. Spoiler alert, this paper is from 2006, they detected nothing and then therefore determined you would need detectors all the way out in about Jupiter and Neptune, so a solar system size detector to be able to find torsion. So I was a little sad. I went, right before this talk about last week, I went to a professor of physics here who studies modified gravity, and I said, I feel so dumb, I was really interested in this idea, no one studies it. He goes, don't be. You had a good fundamental insight. It's not, you shouldn't even call this modified gravity. This is a natural extension of Einstein's field equations, and the reason why no one studies it is because we all accept that it's there. Just, we don't have the detectors for it yet. So being born 50 years later, you could write a paper on this, and you can write a theory paper on this now. So anyways, instead of a paper, I've given a 20-minute talk and spent every Friday of this semester hammering away at a graduate math textbook and feeling very stupid, and hopefully I haven't made too much of a fool of myself. Thank you so much for your time. Thank you.